So you're here, you're at the tedcan.com/statistics. If you scroll down, there's a lot of different options. One of them is the Remind app widget, for lack of a better term. This is if you don't have access to your phone or the Remind app, this is where you can get the Remind announcements. So it's all there. But right above that, I have resources, and I plan on putting more than one file in here throughout the course, which is why I created a folder instead of just posting the link. You'll see a PDF. It's a Desmos stat cheat sheet, because Desmos is not just for statistics, it's for other courses too. This is a work in progress. You can see it starts off with examples that correspond. Yeah, this is clickable. It's just when it's in this form, it's not clickable, which is weird, but that's just how it is. You know, so if I try to click on it here, it's not gonna work. But if I download it and open it, you know, through Adobe or some other PDF reader, then it'll give me the option to click on these links. And so these bring you to examples within the Desmos calculator that show you what these functions look like in action. Some of them are, I'll call them trivial. Like, I don't know how often you're going to need to join two or more lists together, or find the minimum value contained in a list of numbers in this class, right? Because really, minimum is just the smallest number. Usually you could just eyeball that, right? But there were some other ones like that inverse CDF business that we were talking about last time. That's a little on the funky side. You also have covariance. We'll talk about that later in the course. But you know, some of the funkier terms, some probability functions. But here, performing regression, that's where the magic is going to happen, right? Because we could find the correlation between two lists of data, and then we could actually kind of walk through the process. And you know what I will do? I'm going to open this. Do it this way. All right, so good. I was worried that you wouldn't be able to see what I'm doing here. Still not letting me click. Why is it not letting me click? All right, well, I guess I'm going to be posting the Word version of it also, which I could just do right now anyway. So. Let's resume recording. All right, so we're going to learn about something pretty interesting, correlation and regression, because what happens is a lot of folks, they come into a stat class and they're here for a couple of reasons. The most common one is, and it's unfortunate, but it is what it is, and it happens in all forms of education, where it's like sometimes you just got to take a class and get credit, you know? And I look at stat as being the kind of class where even if you don't come in purposely trying to learn something, you may accidentally end up learning something, right? Something that you can find value in the real world, right? We've talked about finding the mean, median, and mode, and standard deviations and stuff like that, and it's all wonderful stuff, useful stuff, but they have their limits. What a lot of people want to do when they're dealing with data sets, and rightly so, is relate those data sets to something else. Now, that something else could be a personal experience, but it could also be, you know, another set of data. And it looks like I got a question coming in, so let me pause the video. Recording. Okay, so what we can do using correlation and regression is determine if there's any kind of relationship between two variables, and even more than two variables. So if I know that, and this is kind of a classic example from a textbook. I verified it to make sure that it was actually true, but as the temperature increases, the number of chirps from a cricket also increases, right? So that's kind of interesting. I mean, I don't know that I would want to do a statistical analysis on it, but that goes in the fun fact of the day territory. You know, so if it's a really hot day, you know, like in the evenings when you hear the crickets and you hear that, like, that buzzing, chirping sound, and it's like ongoing at night. You're like, what is that? Those are just the crickets going a mile a minute, you know? So that's a fun one. You know, you see things like sales of ice cream versus temperature. Like the hotter the days, the more people are going to be, you know, purchasing cold treats, you know, beverages and snacks and things like that. You know, and that's all stuff that I would probably categorize in the realm of common sense. But you could see some other examples here. Oh, I did it. I I got copy pasteitis. Right? Most statistical studies involve more than one variable. Often in the AP statistics exam, that's not you. That's the wrong course. Right? So that's a typo. If somebody needs some typo bonus, just submit it on Remind. All right. Well, anyway, the rest of it is fine. However, there are times where we want to examine relationships among several variables for the same group of data. For example, is temperature outside related to the ice cream sold, which I mentioned? Or does the amount of TV watched affect IQ? Which is kind of a weird one to think about. It's like, if I watch a lot of TV, will that impact my intelligence quotient? Like, you know, don't watch too much TV; it'll rot your brain. You know that old expression. Is that true? I mean, that's really what it's coming down to. Right? So you can take two variables that are seemingly unrelated and see if there is a relationship, a mathematical relationship between them, and then go from there. You know, you could start getting into, you know, gender and voting tendencies. You can talk about a math grade being a predictor of a science grade. You know, or I like the relationship between math and musical instruments. You know, because that old expression of like, oh, you're really good at math. Oh, then you should join band. You know, and when you're in school, because the people who are the best at working with, you know, playing instruments, they're usually strong in math. And it's like, now we got to start thinking about what we call a causal relationship. Will one cause the other to happen, or is it just that they go hand in hand? Like, for example, let's say you have students who are in an honors level math class in high school, and they are also taking band. Are they participating in band because of the fact that they're in honors level math, or does it have something to do maybe with their work ethic? You know, they've spent a lot of time. They're dedicated to the study of math. You know, there's some people out there that are good at math because they chose to be good at math. You know, and we've all done that before, where it's like, all right, well, I got 4 tests coming up. I only got time to study for 3 of them, so one of them's going by the wayside. Which one is it going to be? You know, you make a decision to focus on one class as opposed to another. So maybe these individuals prioritize math and band at the expense of some other class. That's a conversation, you know, and so that's where correlation and regression come into play, right? Because if we plot data points, we can make a determination of whether there's a perfectly linear relationship, meaning like in lockstep, as one increases, the other increases, and it's a predictable pattern. Sometimes it's a strong relationship where one generally increases as the other increases, but there's some fluctuation, and that's okay. And then some moderate would be a looser organization of values where, you know, sometimes they increase, but sometimes they don't. You know, so that's stuff to be mindful of, because if you have a perfect relationship between two variables, then that's great. That's what we want. Perfect linear. That means a linear function is the best model. Like a line equation would be the best model to use as a predictor for the functions themselves. But maybe if you start getting into the moderate territory, maybe a line isn't the best option. Maybe you want to get into like a parabola or a cubic function or a trig function or something like that. These are all sorts of possibilities that start coming into play once you've eliminated linear as a possible outcome. All right, so I'll pause there and check the chat. Which variable is causing the other variable to happen?
Okay.
Okay, so, and that's going to be part of the work that we do, where we say, all right, now that we know that they're related, now let's look at it from the perspective of math causing band and the perspective of band causing math. You know, so it can get a little dicey, but it's definitely the most informative way to do things. Right?
Yeah.
Oh, look at that. Well, that's unfortunate. Okay, well, anyway, the ones that are circled, and I should circle the other one too because it went away when I moved it.
Whoever annotated can hit clear. Oh, it was you. Never mind.
Yeah, so these should be perfect negative, strong negative, and moderate negative. All right, so if you have the handouts or if you're taking notes, then those should be different. Right, and again, typo bonus opportunities. So there's 3 of them right there. So if you need some typo bonus, submit that on Remind and get yourself.
Sorry, last thing, but these are in the same PDF that you have in Blackboard, correct? Like we're going to see your edits here?
Yeah.
All right, perfect.
So I'm going to I'll make the adjustment right here and it'll change, but for future semesters, etc. You want to get it looking good. All right, so let me clear these drawings. Okay, so then we have these other types of functions, the quadratic, the cubic, the quartic, and so on. I only gave the moderate examples because when you start getting away from linear functions, you start getting into the territory of uncertainty. And so when that happens, you start thinking, okay, well, what are the chances that it's going to be a perfect fit? Probably not good. So we start looking for just the moderate cases. But you'll see what I mean by that in a little bit more detail in a few minutes. All right, so there's a couple ways to determine if variables are related. We look at the graph, or we calculate what's known as a correlation coefficient. Right, so we have a graphical approach and a mathematical approach. It depends on the situation. Sometimes you can just get away with the graphical approach. Sometimes you need to do both, and sometimes, you know, depending on the instruction. I would probably. I don't think it's unfair to say that most people go with the mathematical approach as their first option only when they're told to. They usually start looking for the graphical approach solution and go from there. Generally, it doesn't go the other way around where people are looking to do all the math first and then find out, oh, look at that, I could have just looked at the picture. You know, so yeah, there's different avenues that you can take, but I would say that the best way to get started on any question related to this concept would be diagram, graph. All right. So let's take a look at that graphical approach. All right. When we're interpreting a scatter plot, so I'll show you how to make one in a couple of minutes, but when you're interpreting one, you're looking for a few different things. You're looking for any kind of striking deviations from a pattern. You know, so if there's an obvious pattern in a distribution, then you look at it and say, oh, it looks like these all form a straight line. That's wonderful. Oh, they kind of form a straight line, but there's one or two that are a little out of whack. So, oh, what's going on with those one or two? Because those one or two could be what are known as outliers, right? So if those outliers are values that are appropriately present, then you'd have to account for those in some way. But if they're not supposed to be there because they're a form of error, then you would have license to take those values away, right? Remove them from the data set and recompute. Right. You also want to talk about the direction, the form, and the strength. So the direction as in like it's going up or it's going down. The form as in it's linear or quadratic or cubic or whatever. And the strength, you know, strong, moderate, or, you know, I mean, perfect, I guess, would be one of them. But you could start getting into weak territory. I would say that if you're starting to think, oh, it looks like a weak relationship between two variables, then you probably should be looking for a different relationship. All right. Actually, that could mean a lot of things. You know, in the real world, it's like if you're together with somebody and I'm thinking to myself, oh man, I have a pretty weak relationship. It might be time to start thinking about a different relationship, you know, maybe start moving on. It's the same idea here where it's like, linear, it looks really weak. It doesn't look like it's a strong relationship at all. It's not going to stand the test of time. So let me move on from linear. Maybe look at quadratic. You know, and the good really. I know why people, like I was saying before, a lot of people take the class because they just need the credit. And a lot of people take the class because they want to learn, and then everybody else is kind of a mix. Some of us are taking this to get out of other classes, you know, like that's the, I need to get math credit. And so if you're worried when you hear terms like quadratic and cubic and exponential and trig and stuff like that, you're like, wait, I took this class so I wouldn't have to deal with all that stuff. Why is that stuff here? Like, it's not supposed to be here. Get it out of here. Just understand, we're only working with those functions in name only, because the Desmos calculator is going to do all the work for us, right? So if you hear quadratic and you get like you break into like a nervous you know, flop sweat, then I wouldn't get too concerned, because we're not going back to, all right, we're going to make a parabola, let's make a table of values. Desmos is going to do that for us. All right. So when we're looking for an overall pattern or deviation from a pattern, we actually really kind of talk in terms of general terms. So what I would do is I would look at this and say, it looks like, you know, instead of it being, I'm not going to make it too textbooky. I think I could fit a line reasonably through here, except I got this little guy here that's throwing everything off. All right. So what I would say is, it looks like we could say moderate, we could say strong, moderate to strong. You can kind of branch your way through from one category to another. So I would say moderate to strong, positive, linear relationship. I would also I want to get across the idea that that one extra point is screwing everything up. So the way we say that one extra point is screwing everything up is we say that there's a possible outlier. Around 14. All right. So I'm going to highlight these qualifier terms. Because I'm saying it looks like, and it's possible outlier. You really can't pin me down and make me give a definitive statement, cut and dry, black and white, you know, the true, false, like binary kind of thing. There's room for other possibilities here. And so I kind of couch it all by saying, yeah, I think this is what it is. We haven't analyzed it yet numerically, so there's no expectation that I would have a firm final answer. So I say a possible outlier, because if I say that there's an outlier, then I'm making a claim of something to be fact. And I'll even throw in a little highlight on around, because I didn't even commit to it being at 14, you know, because it's not. Based on the scale here, that could be 15 and a half, it could be 16. I have no idea what it is, but I know it's somewhere in the neighborhood of 14, so that's all I would have to say, all right? So when we talk about making conclusions and drawing, you know, or making inferences, sorry, and then drawing conclusions, keep it in general terms, because if you do, then you're not really getting pinned down on the veracity of it, all right? So when I say positive or negative slope, you know, like it's really just going up or down. So this is a positive linear relationship in this particular case, because it's going up. So it goes up. Right? So if I had to slap a line on this one and then slap a line on that one, this one would be going down, so this would be a negative relationship. This one's going up, so it'd be positive. Then we get into strength. I mean, you look at the two possible graphs, one of them, I think, is making a really good case for being a strong relationship. I kind of missed the mark there a little bit. There we go. Those, I would say that this is strong, but you could even use your own terminology. You could say this is very strong. You can throw in a second very if you want. You can say it's very, very strong. You know, because I'm not saying it's perfect. Perfect would be all, like, I drew the line and every single point fell on that line. That's not what happened. So it's not perfect. How strong is it? It's pretty dang strong, right? So sometimes, I mean, right, pretty dang strong if you want. It doesn't matter to me as long as you're getting across the idea that there's some strength here. We can't make a final conclusion, but we do know that it does seem like it's worth investigating. That I don't even know, let's see, average number of heating degree days per year versus average amount of gas consumed per day in hundreds of cubic feet. So it does seem like there's an average between those two average relationships, that it's very strong. That as the number of heating degree days increases, so does the amount of gas consumed, right? And, you know, like, add a little context, I'm basically saying that out of the calendar year, there's only a certain number of days where you'd actually have to use a heat source in your house. You know, in the summer, you don't need the heat. I mean, in theory. But in the winter, yeah, you're going to need it. And so, like, depending on the days, that's going to correspond to a certain amount of fuel that's used. And so what is that relationship? So going into the winter, this would allow me to budget my resources. All right. Now, something else in the next one, father's height in inches versus mother's height in inches. All right. So here I'm going to say no relationship. And honestly, I mean that on so many different levels, because we tend to think in math class that the word that's used in math is not the same as the word that's used in real life, right? So when we say that there's a family of functions, well, it can't be the same as like a family like cousins, aunts and uncles and stuff like that, can it? Well, yeah. That's why we call them families of functions, because they're related. They have common characteristics, right? I can say, in all honesty, like, just at first blush, there better not be a relationship between my mom's height and my dad's height, AKA there better not be a relationship between them, like a family relationship, as in my mom and dad are like brother and sister, cousin, or something like that. That better not be the case. That's not legal, and also horrible. So, like, in that context, I'd say, well, why are we even talking about this? But then you kind of look at it a little deeper and say, okay, well, now we'll just look at the heights. Maybe tall people want to marry other tall people, but I don't know that that's necessarily true, because you see it all the time. And this is anecdotal. I'll say that pretty frequently. Anecdotal evidence is just information that I only know because of my own direct observation. So, you know, since I'm not witnessing everybody's marriages throughout the entire world, I can't make a definitive statement. But, you know, I'm pretty confident that, you know, like, there is variation allowed in there. Like, some folks like tall people, some folks like shorter people, some, you know, different shapes and sizes. So, you know, it could all play out one way or another. So I look at this and I say there's absolutely no surprise that this data is scattered all over the place. All right. So if honestly, I would be more surprised if there was a discernible trend. You know, like, 60-inch tall people that are males, and or maybe not even males and females. I don't know the right way of saying anything anymore. So I'm just going to leave it at that and say partners, individuals who get married. Like, I don't know, does preference come into play? I would imagine that the answer to that is probably yes. All right. And so just because you're 70 inches tall doesn't mean you're locked in with somebody else who, like, Well, let me go online here. Let's get the list of all 70-inch tall people. This is my sample set. This is my set of possibilities. I don't like any of them. Well, I guess I'm crap out of luck. No love for me. It doesn't really work that way. Right? So, I would not there to be a
Professor, in this case, when it's not relationship, it's not line at all. We don't need to mark anything.
Correct. Right. So what we want to do now is start thinking about, okay, now how do we get the numbers? Now, you see all of this, and this is the old school way of doing it. And there's no school like the old school, but this is more for, just giving you a sense of where the formulas that we're about to use in the calculators who do all the work for us, where they originated from, right? So, and even this doesn't really tell the true story. You need to, I just give you a little perspective. At some point in the third unit of my Calculus 3 course, I'll go over where these formulas came from, right? So it gives you a sense of just how complicated it is, all right? So this is really just, originally I put them in my notes to scare people and be like, listen, this is what's gonna happen if you get on my bad side. I'll make you use these formulas. But it really is just like, there are some crazy formulas that we don't have to worry about because the calculator's doing it for us. It's as simple as that. All right. So, and I have steps I didn't take these out because honestly, when I typed up these notes 20 years ago, I thought this was going to be relevant forever. And then, in the spring, it was like, oh yeah, we're doing remote instruction for the foreseeable future. It's like, you know what, we're not using these graphing calculators anymore. So that's a typo. If somebody needs typo bonus, just send it my way. All right. So, because I'll forget to take it out. But what we're going to do is learn on Desmos how you can come up with a few things. The least squares regression line, which is also known as the linear regression line. But a simpler way of saying that, I think, and this is probably the one that people like the most, line of best fit. All right. Line of best fit, it tells you exactly what you're looking for. It's the line that best fits the data. That's, yeah, forget about this other stuff. Let's just go with that one.
Excuse me, Professor.
Yes.
Quick question. So I know in the beginning of the class you said, in addition to Desmos, if we want, we can use graphing calculators. But now it seems like Desmos is really what we're going to be using. So should I, at this point, just put my calculator back in my drawer and just forget about it?
It's up to you, because if you have, there are some people that are really, really comfortable with the graphing calculators to the point where they know them inside and out. I don't want to tell those folks not to use the graphing calculator, but, and these instructions will help you for the graphing calculator, but I'm pretty much going the Desmos route.
Okay, that's fine. I just wanted to make sure I didn't want to keep bringing it out and never use it. So.
Yeah, exactly. No, I understand. That's a good question. Good point.
Okay, thank you.
Sorry, can you just scroll back up to that section for one moment, please? If you don't mind. All right, so linear correlation will either be, it will point in a certain direction, while R squared will simply tell you how strong the relationship is. And
exactly.
It's up to you to determine whether it's negative or not.
Right. And I tend to kind of err on the side of going with the R squared, because I can look at a graph and see that it's going up as opposed to going down. So I don't need a formula to tell me that it's a positive relationship versus a negative relationship. I just need a sense of the strength. And so I like, I'll highlight it here. I like this one in terms of giving us the sense of the relationship, because it just goes by the numbers, and all I have to remember is the closer that R squared value is to the number 1, the stronger the relationship is. And then that's all I really need to worry about.
Professor, I have a question.
Sure.
On the graph, how do you know when it's very strong or strong?
It's just a matter of how tightly grouped the data is. Okay. So if the data is loosely plotted all over the place, then you wouldn't expect a strong relationship. But if they're clustered nicely together around what would be a straight line, then it's going to be very strong.
Okay, thank you.
Yeah, no problem. You see, this table can be also, I mean, as helpful as it can be, it could also be kind of a hindrance and confusing because it's like, well, 0.75 to 1 is my strong interval, you know, just shy of 1, that is. So how strong is strong? You know, like well, if it's 0.99, is that a lot stronger than a 0.95 or a 0.92 or something like that? And so that's where you just kind of go by the look and feel of it, where you look at the picture and say, well, the R value or R squared value is 0.95, and those data points really look tightly packed in a specific area. So that looks pretty strong to me. So yeah, that's why I was suggesting that you throw those qualifier terms in there, like pretty strong or very strong, or you know, instead of going by the book and saying moderate to strong linear relationship, you know, you say this is pretty freaking strong, you know, and go that route, because then you're giving yourself a lot of wiggle room, and you're making it so that, you know, like we're looking at it from a student standpoint in taking a test. How can I take off credit for that? Like you said, it's pretty strong. You haven't told me what pretty strong means. I know that it's pretty close to what my answer ought to be, and so I give you full credit. Right? But let's dive into a particular case. Right? So and we're going to learn how to make predictions using this, but that little section there, making predictions, is useful, but only after we have some functions to work with. So I'm going to say we'll sit tight on this set of instructions here. A striking deviation is nothing more than saying a point that's out of whack. So you look at this one, and you can see that almost all the points are clustered in one central area, but then there's that one that's just out of left field. Like where is that point? That would be the striking deviation. It's one of two possibilities, and we're going to get there. It's one of two possibilities: it's either an outlier or what's called an influential point. Right? So outliers are points that are just off the beaten path, you know, so they're not near where all the other points are. But depending on what kind of outlier it is, if it's too high or too low versus too far to the left and too far to the right, it would be categorized differently because it would have a different impact on the linear equation. But we're gonna talk about that in more detail in a few minutes. So I won't steal my own thunder. All right. So what we need to do is create the graph for these data points. And so you know what I can do, because I want you. So I sent it out on Remind. So it's the that one link on how to get started with regressions, because it's pretty important. It's kind of like a non-starter if we don't have access to that. It's instructional, but I'm going to pull it up here too. Let me just get my page open under resources. Oh, no, it's not resources. Why am I doing it that way? It's here. This can go. All right, so because I wanted it to be on the same split screen so that I can actually refer to it during the lesson. All right, so you get the little overview here. To get started with regressions, you need some data. You got the data from a spreadsheet and put it into an expression in the calculator. That part's fine. That's kind of like up to you. There is the table insert function. All right, so that part's okay. But in terms of coming up with a graph, that's not going to be challenging, because when you plot the points, the graph automatically comes up anyway. So then the question becomes, all right, well, once you have that, how do I come up with a regression equation? Right? That's a little bit of a different story, and it's specifically related to the points that we're using in the table. All right. So you see how the columns, it's kind of hard to see. Even when it's zoomed in, it moves kind of fast, but you can see how it's labeled as X1, Y1. We're going to be referring to the column headings when writing the equation. All right. And so once we do that, then it's automatically going to come up with all the information that we need related to that regression equation. All right. So that's what I'm going to walk you through now. I just wanted you to have a resource, because You know, there is with Desmos and every other form of technology, there's always that learning curve. So what you do is you click on the table function, and you can see it's designated as X1, Y1, right? So the example here says ornithologists, scientists who study birds, tag sparrowhawks in 13 different colonies to study their population. They gather data for the percent of new sparrowhawks in each colony and the percent of those that have returned from migration. Right, so this is the percent of individual sparrowhawks that have returned and the ones that are brand new to the environment. So all I'm going to do is type in the values, 66 and so on. So, you know, just kind of make it something a little bit more relatable. You know, like if you're a parent and you have grown-up kids, those kids, they move out of the house. Some of them come back. And then when they come back, they never leave. No matter how much you try to like gently suggest, yeah, maybe it's time to move on, find your own place. They're like, no, I like it here. I'm like, oh, okay, well, I liked it when you were not here. So so there's that. But then the added component here is, right, so not only does the child who moved out, who is now a grown-up, they move out, they not only did they come back, but they brought a friend with them. That's the percent new, right? So the sparrowhawks that returned, but also some that just came up out of the blue, squatters, right? So that's a little bit of context. You don't really need to know too much about, or you don't really need to know anything about sparrowhawks specifically. You just need to be able to kind of sense that there's a relationship between the two. And it's usually kind of spelled out in the problem. So set this up. I think I bought myself enough time to type the data values in. Do a quick double check, right? It's always the double checking, you know. I try to double check in a way that's different from the way I typed it in initially. Just so, you know, because if I screwed it up the first time, if I check it the same way, odds are I'm going to screw it up again, right? So maybe I'll do a bottom to top, 3820, 4620, 6019. Because really, when we go through this stuff in a minute, you're going to see that the only way to screw this up, as long as you have the, you know, you're taking notes on the process and such, the only way to screw this up would be the data entry part. All right, so that looks good. Data points are in. You say, oh, I thought you said it was supposed to graph it automatically. Well, it does. It's just the values are so large that they're out of the grid. So I just pinch and scroll and all that. So I have my graph there. Great. Wunderbar. Now I just need to get a function. So in the next available area, I'm going to hit that little plus sign again. And you see the f of x. You don't really have to hit that because the default is an indication that you're dealing with a function. It's just I tend to want to do that just to kind of make it painfully obvious to Desmos that yeah, I'm not writing a label. I'm not putting another graph in. I just want to write the equation of a function. So what we do is we type in y, then we use a little tilde, right? You got to kind of hunt around for it, but it's in the QWERTY pad. Right? It's just right next to the comma.
Professor, really quick.
Yeah.
How did you go, like after you entered all the values on the table, how did you get it to a graph again?
I just pinched and scrolled.
Oh, I see. Thank you.
Yeah, no problem. So when you're creating the function, all you're going to do is you're going to type in what the general form of the function ought to be. So a line equation, for example. Line equations are in the form of y equals mx plus b. So I'll jot that down on my notes here. It should be in the form of y equals mx plus b. All right. We know that we're focusing on a line because No, they got all this fancy terminology here, least squares regression line, but within that fancy terminology, least squares regression line, it says line, right? So the equation of a line, y equals mx plus b, right? But what I'm going to put in Desmos is y tilde, because the tilde is telling us that it's an approximate value, right? We're not going for the exact, Desmos thinks in terms of exact or not exact. So if I were to say equals, it's going to try to fit one line to all of these points, which is not possible. What I'm telling it is do the best you can. You know, get as close as you can to grabbing all the points, but if you miss a few, that's okay. So then what I need is an mx plus b, right? And so we can refer back to the process here and kind of see what's going on. If you look at the procedure, you see what it's typing. It says y1 is equal to mx plus b, all right? So it's still in the same form, but it's referencing the title headings for each individual column, right? So that's incredibly important. So here where I'm writing y, because y equals mx plus b, it really should be y1, automatically makes it a subscript, it knows to do that. M, so into the QWERTY pad, M, see it brings up the r squared value. I've given it an incomplete equation, but mx, it still doesn't know what I'm referring to though, because I haven't talked about an x. What I've talked about is an x1, so I get that in there, and then plus b. Right, and then I hit enter, and it locks it all in for me, right? So, you know, it's kind of weird in terms of its display, but it gives us everything that we need, right? So I'm going to do a little, and then one of these, and one of these.
What are residuals?
The next topic that we're going to get to.
Got it.
Yeah, I got a whole explanation related to that. All right, so I'm just kind of chucking this in over here. Let's kind of sneak it in on the side. All right, but you see, we have all that information, and you know, there's some stuff that we don't need just yet, because again, it's like residuals. What's that? Again, we'll get to that in a few minutes. But we do have what we need to come up with a regression equation, but they also give us the r squared value, which tells us, well, in the 0.5 interval, well, we want it to be 1. 1 is the perfect case. The closer you are to 1, the stronger the relationship is. So we're not really close to 1. So I'm not expecting a very strong relationship here. However, they didn't ask us for that, so we're good. Right? So y equals mx plus b. Y equals negative 0.304 x plus b, which is 31.934, going 3 significant. 31.934. All right. Now, it's up to you. You could use the same notation that Desmos used. The only thing that you'd have to do is be consistent with how you describe everything. So, for example, if I were to say x and y here, then I would have to have an x and y here for consistency. But if I wanted to match Desmos, then maybe I say x1, y1 here, so that I can use an x1 and y1 there. Right? That's a matter of personal preference, but in order to be consistent, you want to come up with a way that works well for you. Also, a big question I would imagine is on somebody's mind is what happened to that tilde? Well, that tilde is for Desmos to know what kind of equation you want. We want the equation of a line, and an equation of a line is always in the form of y equals mx plus b. So we do the tilde thing because that's what Desmos understands. But in order to have it in proper statistical notation, we want to have an equal sign. Right? So now, I mentioned this before when I was talking about making predictions. I said I was going to gloss over that because we need an equation to work off in order for it to make sense. Well, now we have an equation. it's saying determine the percent return if the percent new is 25. So what that's asking me to do is, well, percent return is X1. Percent new is Y1. So it's saying determine X1 if Y1 is 25. So what we can do is we can replace the Y1 in that equation with a 25 and solve. But maybe we don't want to. Maybe we want to let Desmos do it, right? So if we're going to do that, then we would want to have a process that allows us to solve an equation. So solve, oops. Oh, sorry, I'm thinking of GeoGebra again. Dang it, I hate myself. Right, so intersect is one of them. Let me just look it up. I always forget. Because on GeoGebra is very similar. So I get the two confused, as we've seen multiple times. So solver, edit. Let's see. That's not helpful. Solve the system. An intersection using the graph. Oh, it's even easier. All right, so I'm going to type in y equals 25. All right, so let me jot that down. All right, because they're telling us that the percent new is 25. So we're going to type y equals 25. So we get a new line that shows up, right? So this new line here, that horizontal line, that's the y equals 25. So what I'm looking for is the coordinates of the intersection between those 2 points, all right? Now, it's kind of weird because you would expect there to be more to it than this, but just by tapping on that intersection point, it tells you the coordinates, right? So we type y equals 25 and then tap on the intersection. Right, and so what we get here is a coordinate. So in this case, it's 22.805 comma 25. That's an x value and a y value, right? We're looking for an x value. So we get the conclusion that x1 is going to be equal to 22.805, 808. Right, and so that's the answer, right? So let me just kind of clarify and re-explain that one, because what it's asking us to do is solve an equation. So what this is equivalent to is you go back into algebra class where it would say something like solve the equation of x squared plus 7x plus 25 is equal to 30. Doesn't matter, right? So what you'd have to do is you'd have to solve that algebraically. And if you tried using your graphing calculator, you'd get a solution, but it wouldn't always be clean. Here, all you have to do is take the left side of your equation, make it as one, make a brand new equation in Desmos to represent just the left-hand side. And then the right-hand side would be another equation, and where they intersect is your solution, right? So this is what Desmos has. It has y equals negative 0.304x plus 31 point, oh, let me move that over. $31.934, and it also has, I also put in y equals 25. So it's solving by tapping on the intersection, it's finding the solution between these two parts of the equation. So it's setting the left side equal to the right side if these two are equal to one another, and then finding the solution. And then all we would need to know, because we know the y value, all we would need to know is the x value from that coordinate, and we have it. All right, resume recording.
Professor, I have a question.
Oh, sure.
So I understand that the percent return is basically x with the, I don't know what you call it, but with the little 1 next to it.
Yep.
Where do you, can you explain how you found that again? Sorry.
So all you're looking for is the intersection between the 2 points. So what I did was I typed in the y equals 25. I typed in y equals 25. I hit enter to lock it in. And then I just go to my screen and just tap on the intersection between the 2 graphs. So where they cross, I'm just tapping on it. You see a gray point shows up, tap on it again, and the intersection shows up.
Okay,
Right.
and then that's the answer. And is it the same for like percent new with the y and the little 1?
So that's the other way around, because here we're talking about percent new. That is the y1 is given to us. I'm sorry, y1 is the one that we're looking for, where x1 is the one that's given to us. This is going to be easier.
Oh, okay, I get it now. Thank you.
I have
No
a quick
problem.
question too.
Sure.
So as you solve x1 as it intersects on the Desmos calculator on the left, so if we were to do that manually, it's saying that the y1 for like example B, set that equal to each other and just solve for x, and you should get the same answer, correct?
Exactly.
Perfect.
Exactly. And usually, I mean, historically, people would ask, well, can we just do that? And for linear equations, I say yes, but then when we get to quadratics and other types of functions, it's just too much of a pain. So, you know, it's definitely worth taking some time to investigate this approach. So I'll take you through C, and then we'll do another example together, just because it is definitely a weird concept. Determine the percent new if the percent return is 90. Right, so they're telling us that the x value is equal to 90. So algebraically, you could do this. So if we're just looking at an algebraic approach, you could figure out y of 90, which would be the same as replacing your x value, 304, with a 90, and adding to it the 934. So we're just looking at that function and replacing the x value with a 90, and then we would get our value. But if you use Desmos to its fullest potential, we can get that solution quicker and easier. Right? So what we do is we just bring up y1 and then tell Desmos, dang it, GeoGebra again, hold on, pause. There's one little quirk when it comes to this. There's always a quirk. But what I'm going to do is I'm going to retype the function in, because it doesn't automatically store it as a y equation. So I'm going to type in, I already used y, so what I'll say is f of x. I'm using function notation. I'm going to write it as, in its rounded form, negative 0.304 x plus 31.934. So all I'm doing is reproducing the equation, and I'll show you what that looks like. Because if I turn off that first one, the regression model, and if I turn off the one I just typed in, you see they both go away. But if I turn one back on or the other back on, they're both going to the same location. So they're the same function. You just have to type it in the second time, which is kind of aggravating, but it is what it is. Right? Now, using my function notation, I can just simply and easily type in the x value that I want, in this case 90, and it'll just spit out the result. Right? And like I said before, yeah, you can do it algebraically, but when we get to the more complicated functions, it's going to be kind of problematic. All right, so so I'll write down the steps here. In Desmos, rewrite the function. as f of x equals negative 0.304 x plus 31.934. Then type f of 90. And that'll give us the result, in this case, 4.574. All right. So like I said, I'm going to take us through another example and you'll see all the bits and pieces, but for now it's just a skill. So it's weird, but I promise you that the alternative is too ghastly to consider. And you've seen the formulas on the previous page. That those are real formulas that at one point, before all this stuff existed, even before the TI-84, when I would teach this stuff, these formulas were how we did it in class, and it was not pretty. Right? And it really sucked because people were getting questions wrong, not because they didn't understand the concept, but because they put a 12 instead of a 13 because they just added wrong. You know, so that's kind of brutal, and we don't want to have to deal with that. All right. So let's take a look at number 2. And like I said, we're gonna just kind of go through this one from beginning to end, and I'll show you I'll show you all this stuff on Desmos a second time around. All right. So I'm gonna wipe this all out, start a new graph, get these points in. So again, table. We want to put our values in 1, 2, 3, 4, and so on. Sorry, not a 3, not a 4. 1, 2, 3, 5.
Professor,
Yeah.
where did you click to get the table? Because I've been trying to figure it out for the
That
long.
little plus sign.
Oh, the plus sign. Okay.
Yeah, then you'll see an option for a table.
Okay, thanks.
No problem. And just be careful when you're typing in values, because if Desmos thinks that it knows what you want to type in, it'll start autofilling. And sometimes it's just wrong. So you just got to make sure. So we always double check. And again, double check in a way that was different from the way that you typed it in. Then pinch and drag. And you can see that these points are pretty spot on in terms of where they're falling, you know. So, I mean, I could zoom out big time, but it looks like I got most of them. So this looks like a pretty linear relationship. Maybe there's 1 or 2 values that are a little out of whack, but not by much. Right? So the question here is saying construct a scatter plot and compute the linear correlation coefficient, determine the linear regression equation between x and y, and then determine if there's any outliers or influential points. And we'll talk more about the outliers and influential points in a sec. But the first part where it says construct a scatter plot. So this is great news for you all, because when we take a test, that test is going to be in an online environment, at least this semester. So you have the ability to copy paste. The nicer way to do it actually is to not embed, but use the share link option from Desmos. So if you've created an account, I've mentioned this, but it was kind of in passing, that your Desmos work is sufficient work, right? So whatever you type in all of this stuff here, like all the work that you type in, you can share that with me, and I'll count that as your work. You don't have to then rewrite it. So when this says construct a scatter plot, yeah, I need to see a scatter plot as part of your final answer, but it doesn't have to be one that you hand created, right? So a paste job from the Desmos calculator is perfectly fine.
How will the test be administered? Is it in like a closed environment? Are we just supposed to hand a PDF back to you? Just like, where will we be pasting it?
There are going to be file uploads on Blackboard.
Oh, cool. Okay.
Yeah. So I try to keep it simple in that regard. So I got my scatter plot. I mean, that was super easy, barely an inconvenience. Compute the linear correlation coefficient, determine the linear regression equation. It sounds like a lot, but that's all the display from the last problem. Like everything that we did there is all going to come up. So it's the same set of processes or procedures. You just got to take note of what your column titles are. It's Y1 and X1. So Y1 tilde mx1 plus b. It gives us the line, it gives us the R squared value. Now this is asking specifically for the linear correlation coefficient. So we're kind of stuck with that. It's asking us for the R value, not the R squared, even though we would prefer to work with the R squared. But that's fine. We do what we're told here. You want to get the question?
It started to be a bother. Can you just do that one more time? I'm trying to walk through it.
Sure.
Sorry.
Not a problem. So let me delete this. So I have my data table, and again, I take note of the fact that it's X1, Y1. So I'm typing in Y1. And then I'm going to go into the QWERTY pad and select the tilde right next to the comma. M times X1 plus B. And then hit the enter, lock it in, and now you have your set of, or your summary information. All right. And that's really, I mean, we've pretty much answered the question, almost all of it. You know, we should be specific because again, it's using Desmos notation here. So we would want to state that our linear regression equation, well, they asked for the R squared or the R value first. So correlation coefficient. All right, so R is 0.999 approximately. All right, so that's pretty dang perfect. You know, it's not 100% perfect, but it's right there. All right, so linear regression equation. So that would be in the form of y equals mx plus b. So y equals 1.643 x plus 1.676. Now, I'm leaving it in terms of x's and y's because the original data table was given in terms of x's and y's. All right, so I'm given that piece of information. So I gotta be consistent with what the problem is framed as. All right, so that's why those are x's and y's rather than x1 and y1s. All right. Now, what I can do here, and so this is beyond the scope of the question, but I know it was a point of concern from the last question. So if I needed to use this information to make a prediction, what I would then have to do is retype my function in as f of x. So again, this question is not asking us to do this, but I know people want to learn how to do it, so I'm doing it anyway. 1.64. We could put as many decimals as they have there. There's nothing wrong with that. X plus 1. You could also put the rounded values to that. I'm fine with that. 629. All right. So we're just retyping it, but using f of x instead of y. All right. Now I like to do a little verification to make sure that I didn't just botch this up. So I'll turn this equation off, and I'll turn the regression equation off, and then I'll turn them back on one at a time and make sure that they're going to the same place. So as long as they're going to the same place, I'm confident that I typed it in correctly. All right. So for example, if this is saying predict x when y is 10, and then I'll make another one. predict y when x is 10. All right, so I'm making two separate questions, but it's all going to be done on Desmos. All right, so to handle this one, highlighting it in this blue color, whatever this is, this guy. If I'm looking for an x value when I know the y value, what I do is I type in the y value as y equals whatever it is. Y is 10. So I type in y is equal to 10. And then all I have to do is tap on that intersection. All right. Sometimes you got to tap on it more than once, but we get there, you know. So type in the y equals 10 and then tap on the intersection. All right, you get an ordered pair. The 5.065 is the x value. Ordered pairs are always x comma y. I already knew what the y was. I typed that in myself. So what we get from this is our answer. So we now know that x is equal to 5.065. So I don't know what this data is referencing, but let's say, for example, it was talking about height and weight. You know, x is height and y is weight. What this is telling me is if an object has a weight of 10, whatever the units are, grams, kilograms, you know, pounds or tons, then the corresponding height that goes along with that weight would be 5.065. Maybe it's feet, maybe it's inches, maybe it's yards, you know, but we're getting the other value that goes along with it based off of that relationship, right? So that's one avenue. The other one is the simpler way. We just type f of 10. All right, that's the function notation, not f times 10, f of 10. So f of 10, and then it'll just spit out what the value is. So we're looking at approximately 18.109. So that's what y is equivalent to. So they told us what x was. We found the y that went along with that. And so that's shouldn't be too bad because it's the same process every time. And, you know, I kind of imagine that people, you know, again, it's remote, it's online, it's all that good stuff. You know, set up your Desmos and save it. You know, you're doing this work. Now save it and call this linear regression example. So when you're tackling a question on a test, call up these calculations and say, oh, okay, that's what I typed this for that, I typed that for that, and now I have everything I need. You know, so there's no concern about like, oh, I don't know what the technique is supposed to be. I don't know how it's supposed to be on Desmos. You'll have it all available to you. Right? We're treating essentially every assessment in this course as an open notes type of assessment. So with that in mind, why wouldn't you have as many quote unquote notes available as you can? You know, and for a lot of us, the Desmos stuff is going to be the only sticking point. So if you can find a way to make that part make sense, then you're going to be unstoppable. Right? Now, it's asking if there's any outliers or influential points. The answer there is no. So, and we will go over cases where there are, but we have no outliers or influential points. I abbreviated influential. That's a terrible abbreviation, but that's what I chose to do. The reason why is because we always look for any striking deviations from the main body of points, and I don't see anything that's out of whack. You know, there's no point that I look at and say, well, everything else is over here, but that point's way over here. I don't see anything along those lines, right? So there's no reason to think that there would be an outlier. And if you don't have an outlier, there's no way to have an influential point, right? Because an influential point is just an outlier horizontally, right? So a point that's deviating in the horizontal direction. So that example that we went over earlier, that had that point that was way off to the right, now that point would be an influential point, because what it does is it impacts the slope of the linear equation. Because when you have a linear equation has two main components, a slope and a y-intercept. The slope is the more important one, right? Because mathematically, for large values, it's going to have more impact on the outcome of a predicted value. Whereas the y-intercept is just your starting value. So it doesn't always have much of an impact. So if you need to make sure that one is going to be well tended to, you would want to make sure that you're taking care of the slope and preserving that and making sure that that's the most accurate that it could be. The y-intercept, you have a lot more wiggle room, right? So that's why we call the outlier in the horizontal direction, we call that an influential point, right? The next problem is so involved that it definitely is not something I want to start tonight. But what I would ask you to do before next class is at least try, because this is asking you to go down the list, quadratic, cubic, and all that other stuff, but at least try this for the linear case, meaning come up with the equation of best fit for just the line, right? So type the data in and then just do it for a line, because what we're gonna have to do, and I'll just kind of steal my own thunder a little bit, we're gonna have to address a line, the quadratic, that's a parabola, cubic function, quartic, exponential, and natural log. So we're going to have to go through all of these possibilities, and it's going to seem like, oh, well, I guess that's going to be the entire class session. Now, it's really not that bad, because the hardest part for any of these questions as we move forward is really only going to be typing in the data set and knowing, like how, what is the method for writing a quadratic equation, a cubic equation, and so on. So there's a lot of information related to that, but if you can just come up with the equation for the line, but type in the equation, the data set, and then come up with the regression equation for a line before next class, then we'll all be in a pretty good starting place. And then we can go from there. And I could show you the rest, and it'll be pretty quick. So next class, we just have to go over this page and talk about residuals, and that's the unit, right? So we're coming down to the wire, which is good, because we have a unit test on the 7th. So it's a week from Wednesday, right? So we're getting closer and closer, but I like to always play it out so that I finish the unit 2 classes before the test, so I can make the class right before the test a full-blown Q&A review session, right? So there would not be any new material on the class session prior to the unit test, right? So we'll get the entire unit squared away on Wednesday, and then next Monday will be open forum Q&A for pretty much the entire session. All right, so I'm going to stop the recording.